The general term graph can be used to describe any data structure that consists of a set of nodes and a set of edges. Now, there are some basic definitions that we looked at, well, that may be important. A graph could be directed or undirected. The way I drew this, I didn't put any arrows on the lines. And that would indicate that as long as two things are connected, then you can actually move from one place to another. Kind of like a two-way street. If a restriction was in place throughout the graph, then we will be putting arrows on the lines. I think I want.
Yeah. Okay.
I think since it's in green marker, I'm going to let the diagram remain in green marker. So we could have a graph that looks like that for argument's sake. Now that would be a directed graph. We also could actually specify that there may be different factors involved from getting from one place to another. So we could put a weight on the graph. Let's say if you're representing a map, you would have different places connected by different paths, by different edges. And one edge is not guaranteed to be the same distance as another edge. So we could actually put a number on the edge, and that number can represent the distance if we're talking about a map. So we could put something like 5, 6, 7, 9, 10. Now, the applications of graphs are very wide. You could actually decide to implement something like a financial management system with a graph, where an edge could indicate the amount of money owed from one person to another. So, and the node would be the different lending entities involved. Now, that's a general abstract concept. Of course, if we're going to be writing programs with these things, we need to have a way to represent them in the computer. And two common ways of representing them are with an adjacent list and an adjacent matrix. Now let's stick with this graph. You will have an adjacent list and matrix inside there. There's one node missing off the adjacent list in that diagram. But I'm just going to draw the adjacent list and matrix of this graph that I have on the board. Stick a pin. There's what I call the weighted adjacent list and the weighted adjacent matrix versus when you just say the adjacency list, by default, you're not referring to the weighted adjacency list or matrix. Now, if there are weights on them, then you would represent those weights with the adjacent list and matrix. Now, I'm going to start by putting the unweighted version of the adjacency list and not the list of the adjacency matrix on the board. And for the adjacency matrix, with a graph of n nodes, we're going to have an n by n array. That's a graph of 5 nodes over there. So we're going to have an array with 5 rows and 5 columns. Now, if I put my from on this side, my 2 on that side. Important if it's a directed graph. I'm going to put a 1 anywhere there's an edge and a 0 anywhere there's not an edge. So I'm going to have a column for A, one for B, one for C, one for D and E, and a row for A, B, C, D, E also. So from A to A, there's no edge, so there's a 0. A to B, there's an edge, so we put a 1. A to C, no edge, 0. A to D, there's an edge. A to E, yes there is. B to A,
No.
0. B to B, 0. B to C,
1.
B to D,
0.
B to E,
0.
C to A,
C to E, 0.
C to B,
0.
C to C,
0.
C to D, C to E,
0. Nothing leading from
D. But D has one thing to C, and everything is zeros. E has nothing coming out of it, so everything from E is a 0. So this is the adjacency matrix for the unweighted graph that we have displayed there. Let's call this G. Oh, I mean, forgetting you. I was remembering your request. I think I have some brighter black marker, so there's a reason that I was using the green, and it was a bit more trusty. So maybe
adjacency matrix for undirected
Unweighted.
graph.
unweighted graph.
Okay. No, it's not directed.
Now let's look at the adjacency list for that graph. So put the adjacent. Now, to draw the adjacency list, we start with a base array. One position in the base array for each node. So we have 5 base nodes, so we're going to have 5 positions in the base array. And actually, it may make it easier to understand if I write these numbers outside of the box, knowing that each position will represent one of the nodes. Now, we're going to have a linked list of the position if there's an edge from that position. So from A to E, there's a node. By the way, the sequence in which you put them doesn't matter. And there's also one from A to D. And one from A to B also. And that's the end of that list, so I think this there ends there. From B, we have one node to C. And there's nothing else from that node to C, so our link list can end there. From C, there's nothing off there. So our linked list would not even start with a null pointer right there. From D, there's 1 to C. And from E, there's nothing out also.